Today, we are definitely very glad to have in our seminar series Professor Mandar Chitre. Mandar is currently the head of the Acoustic Research Laboratory at the Tropical Marine Science Institute and Associate Professor of the Department of Electrical and Computer Engineering at the National University of Singapore. Prior to joining the Acoustic Research Lab in 2003, he headed the technology division for a Singapore-based telecommunication software company for 5 years. Mandar was awarded a PhD by the National University of Singapore for his research in the field of underwater acoustic communications in shallow waters. Prior to this, he obtained a master's degree from the National University of Singapore, developing simulations and algorithms for ambient noise imaging, and another master's degree in bioinformatics from the Nanyang Technological University. Mandar's research interests include underwater acoustic signal processing, underwater communications and networking, ambient noise imaging, and cooperative underwater robotics. So today, he will give a very interesting seminar on unusual suspects, a tale of discovery of less known but critical challenges in underwater communication. So thank you again, Mandar, for joining this seminar. And I remind all the attendees that you can write your questions on the Q&A panel, and at the end, Mandar is very happy to reply to your questions. So I leave you the stage. Thank you.
Thank you, Julia, for the very kind introduction, and thanks for organizing this seminar. So one of the things that I have been interested in over the years is to build underwater networks. So not just point-to-point communication links, but networks just like we have internet to extend that underwater. Now, doing that has not been easy, and we have been at this for, I guess, a good part of 2 decades now. So what I'm going to talk about today is some of the discoveries that we have had, or at least the realizations rather than even calling them discoveries, of less known but critical challenges in underwater communication. So a lot of people have already done very good work in underwater communications, and there are a lot of very well-known challenges and good solutions to them. But I want to focus on a couple of the ones that are a little bit less known, but they are critical in many areas for underwater communications. The key lesson that I have learned in all of these years of working with underwater communication is that you need to understand the physics and not fight the physics, but rather use the physics in order to get better performance. Examples of this include some of the work that I've done on impulsive noise, communication and impulsive noise, and I'll be talking about that today. And also some of the work on propagation delays, which I won't be talking about very much today because it focuses on the network layer. Today's talk, I'm going to try and focus mostly on the physical layer, because having a good underwater link is the basis for having a good underwater network at the end of the day. So today's focus would be the 2 challenges, somewhat less known ones, for underwater communication at a link level. So before we jump into looking at what the unusual suspects are, what are these 2 challenges, let's start off by looking at what the usual suspects are. So if you pick up any paper on underwater communication, you probably are going to see at least a subset of some of these, the list that I have here. You might have adverse sound speed profiles, because of which you end up with very complex propagation conditions. You might have excessive reverberation in shallow waters, so a lot of multipath, which you will very commonly see people talking about. You might have a time varying channel, and therefore estimating the channel and dealing with it can become quite tricky. One of the unique features about the underwater channel is the fact that we get not only wideband Doppler, but often different paths may have different Dopplers, and therefore you can get multi-scale Doppler from sea surface motion. If you're working in areas where you have significant surf or breaking waves, then you might have attenuation because of bubbles. There can also be noise. So you may be working in areas where there's a lot of ambient noise. And at a physical level, the long propagation delays can also make a difference because it limits how much channel state information you can pass to the transmitter in order to do things like adaptive modulation. So these are what I would call the usual suspects, things that have been very extensively addressed by many, many researchers with good solutions and a lot of literature about this. Now, I don't mean to say that these particular challenges are less challenging than the ones that we're going to talk about. In fact, these are very challenging, but there is a lot of work that people have done on overcoming them. So rather than talk about these challenges, I want to talk about two of the challenges that we have faced where there is relatively less work and they are less known. So what exactly are these, what I call unusual suspects? In order to understand that, the first thing that I need to tell you about is a little bit of the history of the work that we did, where we got to there from, and therefore you will understand where these particular challenges came from. So, as I said, I was interested in building underwater networks, and I live and work in Singapore, so I was interested in building underwater networks around the port of Singapore. When we started on some of this work back in the early 2000s, we were not doing research on underwater communications, but rather we were a user of underwater communications, so underwater modems, in order to build networks. Now, the expectation was that in the port of Singapore, where we have very well mixed waters, we have relatively mild winds. It's warm, shallow waters with a lot of shipping, but in general, the conditions are somewhat benign. We don't get a lot of winds, we don't get a lot of surf, we don't get a lot of white capping. The temperature throughout the year is almost the same, so you don't get a lot of sound speed profiles. What one would expect is that challenges such as complex conditions because of sound speed profile, or even the time variability of the channel, or having multi-scale Doppler because there's not a lot of waves, or attenuation because of bubbles in the surf zone, these problems would be relatively small, right? And so I would expect that if you get a modem from other waters here and you operate it, it should work quite well, maybe even better than what it would in other waters. So what was surprising to me is that when we tried this with many commercial modems, we found that the performance that we could get in Singapore waters was significantly lower than what people were getting in other waters. And that was not only frustrating, but it also drove my curiosity as to why is this? What is it that causes these waters to be challenging? In fact, it turns out that Singapore waters are probably one of the most challenging waters in the world for underwater communications. So what is it that drives this? And so that started my interest in underwater communications, and I started looking at this problem in more detail. So the two things that I call unusual suspects are probably critical in understanding what happens in Singapore waters. So it's not that any of the challenges that I listed earlier are not there in Singapore waters. They are. Many of those challenges are there. You still have fairly complex propagation environment because of having islands. You do get a fairly long multipath delay spread, but it's no longer than what you get in other waters. What's unusual, one of them is the fact that we get a lot of impulsive ambient noise because of snapping shrimp. Now, it's not just related to Singapore waters. You do get that in many other waters, but probably not in many waters where many of the initial work on modems and underwater communication was done. And perhaps that's why this was a less well-known problem. The other one, and this actually took us a much longer time to get a grip on, was the fact that Singapore water seems to have a persistent microbubble layer because of ship wakes. We get a lot of shipping in Singapore waters. And I'll show you how what exactly happens in this case down the road in this talk, right? So impulsive noise because of snapping shrimp and persistent microbubbles because of ship wakes are the two big challenges that I want to talk about today. Now, in a way, you could even say that this is at the end of the day, a single challenge in the sense that it is all because of bubbles of one sort or the other. Because it turns out that snapping shrimp make impulsive noise by actually creating small bubbles which cavitate and collapse under their own, under the pressure of the water around it. And so the impulsive noise because of snapping shrimp is also a result of bubbles. So let's first start looking at snapping shrimp noise. So for those of you who are not familiar with snapping shrimp, these are small little creatures, maybe an inch or two in size, that live in many places with shallow, warm waters. So you find them around Singapore for sure, but mostly around Southeast Asia. You find them around the northern parts of Australia. You also find them around the Mediterranean in some places. You find them in on both coasts of the US in the southern waters, so around Florida and in San Diego. You find them in Brazil. So there are a lot of places in the world where you get quite a lot of snapping shrimp. The snapping shrimp basically have a large claw that you can see here. And what they do is when they rapidly close this claw, it shoots out a jet of water in front of it. This causes a tiny gas bubble to form, and there is low pressure in the gas bubble, so it collapses under under the pressure around it, and that collapse makes the sound. Now, snapping shrimp use this for stunning prey. They may be using it for other aggressive behavior or perhaps even communication. So they have many uses for it. But when they create this bubble, the collapse, the sound that it makes is very broadband. So it affects communication systems at many different frequency bands. And at the point of collapse, the temperature inside this bubble reaches the surface temperature of the sun, about 5,000 Kelvin. So it's a lot of power that's packed into it, but not a lot of energy because the collapse only lasts around 100 picoseconds. But the sound that it produces competes to be among the loudest sounds in the that's made by any creature in the ocean. And the competitor for snapping shrimp are things like sperm whales. So they are very loud. Now, an individual snap, while it's loud, it wouldn't matter too much because it's very, very short in time. But there are millions of these snapping shrimp that live in crevices and in burrows around warm, shallow waters. And so you get a lot of these snaps per unit time, and therefore you get a lot of noise. So some of the work that we've done at the lab has been in characterizing the habitats and actually looking at how many snapping shrimp you have. And what we've found is that you might get somewhere between 10, a snap every 10 seconds to 100 seconds per square meter of area that you're monitoring. Now, if you have a large area from which you're hearing snaps, that's actually many hundreds of snaps a second that you might actually be hearing. So let me show you a short time series. So this is a 1 second long time series that's been recorded in Singapore waters. And these vertical lines that you see, these are pressure, large pressure that you get because of snapping shrimp. So you can see that even just in 1 second, you can see a very large number of snaps that can be recorded if you just put a hydrophone in the water and record. You can also see that the time series that you see here looks very non-Gaussian. So it's very far from being Gaussian-like. These impulses cause the probability distribution to significantly differ from the Gaussian distribution. And this will have a profound impact on how you communicate or how well communication systems work in these waters if you don't take into account the non-Gaussian nature of this noise. On the right, you can see a power spectral density. And what we have in here is the power spectral density that is typical of snapping shrimp. You can see that this is very broad. So while it peaks at a few kilohertz, even going up to 100 kilohertz or so, the dominant source when snapping shrimp are around is snapping shrimp. So other noises like shipping noise, etc., dominate the low frequency, but as you go to high frequencies, snapping shrimp noise tends to dominate in warm, shallow waters where snapping shrimp exists. And the solid line here is some of the observed spectra of noise in Singapore waters. You can ignore the peaks here, which were because of certain local noise conditions, but this overall shape is basically what you see of snapping shrimp noise. So it reduces as a function of frequency, but at high frequency, snapping shrimp tends to dominate. So what does non-Gaussian noise mean here? So let's take a small section here. So here the time series of just 100 milliseconds in there. And if I take the pressure that you are seeing and plot a probability distribution of it, this is what you would get on the right. Now, you might be used to seeing probability distributions with this on the x-axis and this y. We have put it on its side so that you can see that this pressure here is what's plotted on the y-axis, and the probability density is plotted on the x-axis, and it's plotted on a logarithmic scale. Right? So the histogram here shows what real snapping shrimp data looks like. Right? If I fit a Gaussian distribution onto it, this is the curve that you get, and you can see that it's actually a fairly poor fit. It tends to be broader than the actual distribution in the center, because these heavy tails that you get for the distribution tend to overestimate the variance of the Gaussian. On the other hand, if you look at the probability distribution in the tail areas, the Gaussian distribution severely underestimates it. So the Gaussian distribution thinks that most of the pressure is going to be around here and not very much up there. Whereas in reality, you actually have much heavier tails. So the distribution that tends to model this much better is the symmetric alpha stable distribution. And I've shown a fit of the symmetric alpha stable distribution here. So that actually models it much better. So why is it that Gaussian noise or additive white Gaussian noise is a ubiquitous model? One of the reasons why it's a ubiquitous model is a theoretical reason that people appeal to the central limit theorem, saying that, if you don't know very much about the noise and you have a lot of noise sources, when you add them together, you tend to get Gaussian distributions. The other reason is Gaussian distributions are mathematically very tractable. So they are very attractive from a signal processing standpoint to work with. But when you see these kinds of distributions, and it's very clear that these are non-Gaussian distribution, one has to accept that, because if you don't, then you get a mismatch with the model, and that leads to poor performance. So the distribution, the symmetric alpha stable distribution, actually has a very strong theoretical foundation as well. So there is a generalized version of the central limit theorem, which basically says that if you have very high variance noise, so basically noise which is very impulsive, and you add a large number of them together, you will converge to a symmetric alpha stable distribution. So there is a good theoretical basis for it as well. Now, one of the things that's interesting to think about, and this was something that confused me when I started looking at it. So we do know that for a class of distribution where you have finite variance, the Gaussian distributions have the highest entropy, which means that if you deviated from the Gaussian distribution, and if you had a finite variance, which for real measurements, there should be a finite variance that you would expect because there's a finite energy that's available. You would think that the entropy of the noise must be lower than the Gaussian entropy, and so you should have better performance, not worse performance than Gaussian noise. So the worst performance comes from a mismatch with model, not something that is physically required, saying that because you have impulsive noise, you must have a worse performance. Now, it's a little bit tricky to apply this to symmetric alpha stable distributions because they tend to have a infinite variance in theory, but practical distributions for snapping shrimp noise, while the symmetric alpha stable distributions are good approximations, the practical distributions do actually have a finite variance. And so one would expect that if you have good signal processing, you might do better than what you can do with Gaussian noise for the same variance noise. This is actually clear from some of the early results that we have. So this is a figure that I've taken from a 2006 paper, where we looked at different signal processing techniques and how they perform in snapping shrimp noise. So here we have used recorded snapping shrimp noise, added different signals to them at different SNRs, and then looked at what a match filter, which would be the standard technique of detecting a signal in it would do, versus some of the more optimal techniques. So this line here basically shows the signal processing based on a Gaussian noise model. So if you assume a additive white Gaussian noise, a match filter turns out to be a linear correlator, and this is the performance that you would get out of it. So it turns out you would need somewhere between 15 to 20 dB of signal to noise ratio before you will start getting good probability of detection at a probability of false alarm of 10 to minus 3. On the other hand, the ML here, which is this top curve here, is a maximum likelihood estimate based on knowing the distribution of noise and doing a maximum likelihood estimation of the signal. And you can see that there is something like a 5 to 10 dB difference in performance if you use the correct signal processing. Now, the maximum likelihood estimation is actually quite difficult to do in practice. You can do this offline, but doing it online is computationally too intensive. Also, it requires you to know exactly what the distribution is. Whereas the linear correlator or the match filter does not require you to know the exact parameters of the distribution. All you require is to know that it is a Gaussian distribution. So it turns out that there are other techniques, and the two techniques that I've studied here are the sign correlator, written as SC here, and the LO, which is the locally optimal detector. These are relatively computationally simple techniques. In fact, the sign correlator is computationally even simpler than the match filter. And so they are computationally simple. They don't require you to know the exact parameters of the noise distribution. They only require you to know that the noise distribution is impulsive. And they can give you a significant improvement over the match filter if you are working in impulsive noise, in this particular case, snapping shrimp noise. If you were working in Gaussian noise, however, these curves would be actually on the other side, or rather this curve would be on the other side of this. That means the signal processing based on Gaussian noise model would actually do better than a sign correlator if you were working in Gaussian noise. But once you are working in impulsive noise, this is much better, 5 to 10 dB better. So to understand what exactly is happening in here, let's take an example and work through it. So the example that I'll work through is I generate some Gaussian noise, white Gaussian noise. And in this case, it's normalized. So it's got a unit variance noise that I've generated. So this is completely synthetic noise that's been generated. If I take this noise and I pass it through a match filter for a particular signal. Now, this is purely noise. There is no signal in there. I would not expect to see any peak for the signal, but I would expect that at the output of the match filter, I would get certain distribution of the match filter output, and I would use that in order to set a threshold for detecting a signal. So this, when I pass through a match filter for a known signal, this is the kind of output that I get. So here you can see that this is randomly distributed. But if I wanted a low probability of false alarm, I might pick a threshold of say 200 or maybe something a little bit lower than that. And anything that crosses that, I could say that, well, I might have a signal in there. And we'll look at some of the outputs with signal in a short while. Now, if I do the same thing with recorded snapping shrimp noise. So here's a snippet, 8-second snippet of recorded snapping shrimp noise. And it's normalized such that this has a sample variance, which is also 1. So this has a sample variance of 1. This has a sample variance of 1 as well. So they are equivalent in terms of the signal to noise ratio I would get if I added the same strength signal to this and the same strength signal to that. What is worth observing here is firstly that while you do get very large deviations in here, If you look at this region in between, this actually looks smaller than this. So the distribution, as we had seen earlier here, if you remember here, so this distribution is narrower than the equivalent Gaussian distribution. So that's essentially what you are seeing in here, that the center of this distribution is narrower than this, but you have very heavy tails. So you have a large probability of getting deviations from there. And when you pass this through a match filter, what you get is something like this. So again, the typical value that you get is actually smaller than this. So I could set a smaller threshold, but then I would get a very large false alarm rate, because there's a high probability that some of these peaks that you are randomly getting, these are not real signals. These are just snaps, which are causing the match filter output to give you a large value. These peaks would cross the threshold. So I need to set a threshold which is up here, much higher than the threshold I would have had to set here, to get the same false alarm rate on both of it. And if I did that, then I would require a detection that is much stronger in order to be able to detect that signal in snapping shift noise, whereas I could very easily detect it in Gaussian noise. So that's what the essential problem is. So let's next add a signal in here and look at what the output looks like. So when a signal is added, you can't actually see very much on the time series here or here. So there's actually a signal that's been added early on in this time series. But when it passes through a match filter, you can see a clear peak in here. Right? You can also see the same peak in here. So this is the peak which relates to the signal. So if I actually go backwards, you'll see that this peak wasn't there here. And when I add the signal, this peak appears. So this peak is related to the signal, but I can't differentiate it from some of the other peaks. And therefore, I would not be able to detect this in snapping shift noise. So that's essentially what the problem is that we need to solve in order to get good detections in snapping shift noise. So what techniques like the locally optimal detector or a sign correlator do is they take this signal, and instead of passing it directly through a match filter, they first pass it through a nonlinearity. A nonlinearity such as just taking the sign of it. That means anything that's positive becomes +1, anything that is negative becomes -1. Right? And then you pass it through a match filter. If you did this and you look at the output, this is what the output looks like. So now you see that a lot of these peaks that were there because of the snap, they disappeared. And they disappear basically because they had high value, but they just became +1, just like these small values were +1. So we have essentially clipped away the snaps. And so that causes all of these ones to disappear. But the signal stays, and that's mainly because the signal has a large number of zero crossings which are in the correct place. And so the positives and negatives are aligned with the signal, and so you get a good peak for it. This peak is smaller than the original peak. And this is mainly because the nonlinearity not only distorts the noise, but it also does distort the signal. And so it reduces the correlation of the signal, but it damages the noise a lot more. And so it removes all of these peaks, whereas the signal still has fairly appreciable peak. And so you can set a threshold, let's say here around 200, and quite reliably detect the signal. So that's why something like a sign correlator or a locally optimal detector works quite well in snapping shift noise, whereas a standard match filter doesn't work that well. So what's the end result of that? If we look back at this plot that you have already seen, you essentially see this improvement that you get from the sign correlator, the locally optimal detector, and this is the maximum likelihood. The locally optimal detector actually works very close to the maximum likelihood curve. In fact, they are indistinguishable in this case. And the sign correlator is very simple. It's a 1-bit correlation, and it only has about a 1 dB loss as compared to the optimal performance that you can get in snapping shift noise. Now, while this is a great success in the sense that if you wanted to do detection of preambles which are related to communication signals, this would be very useful. You can do this in passband. But a lot of the real signal processing that we do in communication systems is done in complex baseband. And so this passband methods can't so directly be applied. You need to do something more. So in order to understand how the propagation noise affects baseband communication systems, we first need to look at how do you do the conversion from passband to baseband. There are many different techniques of doing it. In Gaussian noise, they tend to be equivalent. There is not a significant preference of one technique over another. But it turns out that in propagation noise, the way you do the processing makes a large difference. I'm going to pick one of these techniques to illustrate the point. This is a technique where it's intuitively easy to understand what is happening. But we do have some papers that you can refer to understand some of the other techniques and what the impact is. So the technique that I'm going to look at is a down conversion, where we do a down conversion to baseband, where the carrier frequency and the passband sampling rate have this relationship. That is, the passband sampling rate is exactly 4 times the carrier frequency. This is a common choice that's made in many communication systems, because for this particular choice, if you look at the baseband conversion, when you multiply by a complex exponential, you end up with sine and cos terms, and the sine and cos terms just become 0, 1, 0, -1, and so on. And so you get a very simple formulation which can easily be implemented on FPGAs or DSPs without requiring floating point operations. So it's a fairly common technique to use. Sampling rate is 4 times carrier frequency. So I'm going to look at this particular technique. And it turns out that this technique is very good to intuitively understand what happens with propagation noise. So what's illustrated in here is a time series. So I've just taken a few samples and I've called them A, B, C, D, all the way to K. So think of each of this as one passband time sample, and this is at whatever sampling rate the passband sampling is. Now, when we multiply this by a complex exponential, you're going to get a real part and an imaginary part. And the real part is going to be the cosine term, and the imaginary part is going to be multiplied by the sine term. When you do this, because you're going to be multiplying alternate samples by 0, and here you're going to be multiplying alternate samples by 0, what you effectively get is each of the samples, let's say sample A is multiplied by 0 here, so you get 0 here, but it's multiplied by 1 here, and so sample A goes in here. Sample B, on the other hand, is multiplied by 0 here, so it doesn't contribute here, but it gets multiplied by 1 here and contributes here. So it's either multiplied by plus or -1, so you get either, so the alternate samples you get in the imaginary channel, and the other alternate samples you get in the real channel. Now, while doing down conversion, we usually also do a downsampling, and before you do the downsampling, you need to do some kind of a low-pass filter. So I'm going to take a very simple example here. The actual low-pass filters you might use would be more sophisticated. But just for the purpose of illustration, I'm going to take a low-pass filter where all I do is I'm going to do a downsampling by a factor of 2. And the low-pass filter is just going to be taking the 2 samples that you're going to downsample for, average them, and multiply it by 2. So the multiplication by 2 is just a scaling factor so that I keep the mathematics here simple, but it's essentially averaging every 2 samples here. So these 2 samples would get averaged to form 1 sample, these 2 samples would get averaged to form 1 sample, and then same for the next 2 samples and so on. So when we do this, the low pass filter plus downsample goes in here, and so I end up with these as my real parts, these as my imaginary parts. So the first sample would be A plus IB, next sample would be minus C minus ID, and so on, right? So these are the complex baseband samples I would get. Now, when you do this, recall that every sample in here either ends up in the real portion or in the imaginary portion, but they are mutually exclusive for this particular choice of 4FC. Right? Which means that if all of these samples, if they are independent, you would get some kind of a distribution, a joint distribution of these two, and you could plot this. So if I plotted this for white Gaussian noise, so I pass this through the basebanding process, I can plot real on the horizontal axis and imaginary on the vertical axis, and you would get a spread that looks something like this. So it's circularly symmetric. And these are the kind of noise at baseband that we are used to seeing. So if you look at a PSK constellation, you have a point at a particular constellation point. When it goes through the channel and you add Gaussian noise, we do expect that noise to spread, and you would see these kinds of distributions, which is a circularly symmetric spread that you see around the constellation point. So this we are very used to. So this makes an assumption of a wide Gaussian noise. So the Gaussian, the probability decays off very quickly as you go away from where the center was. And so you don't have a high probability of getting a large deviation, but you have a quite large probability of getting small deviations from that value. Let's do exactly the same thing, but we will do this with whitened snapping shrimp noise. Okay, so why whitened? And I'll tell you exactly how we did the whitening. But whitened mainly because I want to make a comparison with the white Gaussian noise. So white here refers to the fact that you have a flat power spectral density, but it also refers to the fact that every sample is independent of every other sample, right? So there is no time dependence between the samples. So here in real snapping shrimp noise, there is time dependence because when the snaps occur, you might get multiple samples, so the noise is bursty. But in order to do a whitening, what I have done in here is I've taken real snapping shrimp noise, but I have just shuffled the samples randomly. Now that would not happen in a real communication system. So this is contrived, but it is to illustrate a particular point. Once we understand that point, we will go back to real snapping shrimp noise and see what happens with unwhitened noise in a moment. But for now, just bear with me and let's look at what happens with whitened snapping shrimp noise. So this is the whitened snapping shrimp noise. And if I go through the same process and I plot it, what you will see is this is not circularly symmetric. It has this diamondish shape, but not only just this diamondish shape, it's got these long tails in particular directions. So what's happening in here? What's happening is that there is a fairly large probability of getting a deviation from zero for a impulsive noise distribution. However, the probability that if one of them deviated from zero quite a bit, the next one will also deviate from zero quite a bit is relatively low because most of the distribution is still centered and the mass is around zero. And so you can get a deviation in one direction along the imaginary or real axis quite large, but having a deviation in both directions, the probability is quite small. So you get less probability of getting large deviations in these directions, but you have a large probability of getting large deviations in these directions. And this is coming from the fact that every sample was either going into the real part or the imaginary part. So to have both of them be large, I would need two large samples, one after other. And the probability of having that for white snapping shrimp noise is quite low. And so you get these four-tailed distributions that you get for the special case of downsampling by a factor of 4, or down converting by a factor of 4, where the carrier frequency is 1/4 the sampling rate. Now, what's the implication of this? If we did have noise that looks like this, let's look at what happens with a very simple BPSK constellation. So if I had a BPSK constellation where I was placing my two PSK points in the real imaginary plane at these 2 points, this is what I would receive with the additive white snapping shrimp noise channel. You would get a distribution that has this characteristic shape. And the way these tails are pointed, in this direction, it wouldn't matter too much, but in this direction, this tail is pointed right at this constellation point, which means there is a quite large probability that some of the, if I transmitted this particular constellation point, I might mistake it for this one because it might cross the vertical axis here. The same thing for here. And so you get a relatively large bit error rate for this kind of a constellation. But there's a very easy fix. If instead of using a BPSK, which were placed like this, what if I use BPSK, which are placed like this? These are still 180 degrees apart. So it is a valid BPSK constellation, but it just rotated by 45 degrees. If I did that, now the tails don't point at each other. In fact, the probability of having this constellation point be confused as this one becomes quite small, because the tails are in directions where your decision boundary is going to be like this in this case, right? So you can get significantly better performance than what you might get with Gaussian noise. It also turns out that in order to rotate this constellation like this, you don't even need to do anything on the transmission side. You can do this rotation completely on the receiving side, because the position of these constellation points is just a function of how you are doing the synchronization at the receiver. So if you just delay your samples by a little bit, then this constellation rotates, right? So you can have a phase lock loop which locks onto the carrier, and then you just do the sampling at a slight delay from the where the lock is, and that will allow you to recover a constellation of this sort at the receiver, and you would get much better communication performance than you would get even with Gaussian noise in this particular case. So the key point that I'm trying to make here is that once you understand what the distribution looks like, and once you get rid of a lot of our intuition that is based on Gaussian noise-based signal processing for communication, and you start looking at what happens with impulsive noise, you can actually make very small changes to the communication system and still be able to do pretty well, or perhaps even better than what you can do in Gaussian noise. So here is where you're now starting to get a improvement over Gaussian noise, which is what you might expect from a information theoretic standpoint, because the entropy of the snapping shrimp noise must be less than the equivalent Gaussian noise for the same variance. Now, in this case, as I said, because I'm looking at a white snapping shrimp noise channel, this is a bit contrived. You don't actually have white snapping shrimp noise. If you looked at the power spectral density of snapping shrimp noise earlier, you might remember that there was a fall off with frequency, and that is related to the fact that you have consecutive samples which are correlated. They are not uncorrelated with each other, that they are not independent of each other. And because they are not independent of each other, there is actually a higher probability of even getting some noise in these directions. So you don't get this four-tail distribution exactly like this. But instead of that, if I use real snapping shrimp noise, pass it through the basebanding process, you get something like this at the output. So you can still see that this is not circularly symmetric. You can clearly see the diamond shape. You can also see the tails. They are not as clear as the white snapping shrimp noise, but it is clear that if you go in these directions, the probability of having noise in this direction or this direction is much higher as compared to, let's say, this direction. You have much lesser points here, or you have much lesser points here, or you have less points here and here. So there is still a benefit of placing your constellation points correctly, but the benefit is not as large as what might be what one might think based on white snapping shrimp noise. But this kind of signal processing is some of the things that we do in our modems now, and we do get significantly better performance when we implement this. Now, how big a improvement you would get is very heavily dependent on the frequency band that you're working with and the bandwidth that you're working with. So the higher the bandwidth and the higher the frequency, the larger the advantage. At low frequency, and if you have relatively narrow band, the difference is not very much. This distribution tends to become more circular as the bandwidth becomes small or the center frequency becomes small. So this is a plot that I've taken from this paper that we did, looking at summarizing what some of our findings were in terms of baseband conversion. So I'm not going to go through the details of what different baseband conversion techniques here are, but the key point that I want to make from here is that if you have signal processing based on Gaussian noise model, you might get a curve that looks something like this, where you have signal to noise ratio, or energy per bit per noise level, and BER here. So the BER does reduce with increasing signal to noise ratio, but it doesn't reduce anywhere as quickly as it would if you had signal processing based on the correct modeling of impulsive noise. Now, this signal processing tends to be computationally very intensive, so it's very hard to implement in real systems. But there are intermediate baseband conversion techniques that we can have. These are linear baseband conversion techniques, which are quite easy to implement, and they can fall somewhere in between the two. So you can get a significant advantage in terms of BER performance. So here, let's say at a BER of 10 to minus 4, you might get a 13 dB advantage as compared to the traditional baseband conversion techniques versus some of the baseband conversion techniques that we have developed, which are specific for impulsive noise. Now, this just gives you a glimpse of some of the work that we have done on snapping shrimp noise and signal processing and communication systems. A lot of this work was done by one of my students, Ahmed Mahmood. So you'll see a lot of his papers. So he did his PhD looking at this problem and developed a lot of techniques which are documented in a number of papers. So I've just left a bibliography for you here in case you are interested in this area. These may be good starting points to look at how you can improve communication performance in impulsive noise channels, not necessarily just in snapping shrimp noise channels, but also impulsive noise because of other reasons. And I'll talk about some of the other kinds of channels where you get impulsive noise later on in the presentation. This now brings me, yes, Julia.
Thank you so much.
Julia, I still have the second part of the presentation where I'm going to talk about bubbles.
Okay, yes, maybe we can move forward. I see already some questions, but maybe if you want to move forward, we can reserve all the questions now for the end.
So I will probably have another maybe 10 minutes or so, and then maybe we can take the questions. Does that work?
Okay, sure.
Okay, great, thanks. Okay, so let me second talk about persistent bubbles, and I will go through this a little bit quicker. So understanding snapping shrimp noise was some of the things that we did in the very initial part of understanding the communication channel in Singapore. But understanding persistent bubbles, or the fact that persistent bubbles is a problem, took us a much longer time. It took us a much longer time because what we found is once we had solved the snapping shrimp noise problem and we had used a lot of techniques that people were using, we often got very good performance in Singapore waters, but not always. Some days were good, some days were not good. And we were trying to understand what the difference between those days were. And it was not that straightforward. It only became apparent when we set up a long-term test bed where we started measuring data over years. So we had a test bed which we ran for about 2 years. I'm going to present some data from about a 24-day data set from here, where we communicated between two modems continuously every few minutes, and we observed how the performance was and looked at what some of the parameters were. So I'm going to focus on the data for a 600-meter channel in here. And what you will see is that there's the place where we were doing these measurements, we had a lot of shipping traffic. So every dot here is an AIS transmission from a ship over a 24-day period. So these are all the ship transmissions you get. So we had ships passing by nearby, and we were not through the channel very much, but just nearby. And we were looking at how the communication performance is. So we had two nodes, one bottom mounted, one surface mounted, and they were transmitting every few minutes. We had over 75,000 transmission over a 24-day period in the 18 to 30 kilohertz band. And we had many different types of transmissions, but I'm going to focus on the HFM1 transmission, which is a hyperbolic frequency modulated upsweep for the purposes of today's discussion. So let's look at what we get in here. So I'm going to take a 4-day period over which we look at what the HFM detector output looks like. So high values in here is good detection, low values are bad detection. And you can see that there is quite a lot of variability over a period of 4 days. The suns here mark 12 p.m. on 4 days, and this horizontal axis is time. Right? So the first thing that you notice is that there is some periodicity in here. And if you look at just a 1-day period, you will see that there seem to be 2 peaks and 2 troughs. So there seems to be some kind of a twice-a-day period in here. So the first suspect from here is maybe it's the tidal height that makes a difference. And so I plot the tidal height along here, and you start looking for correlations. What you find is that actually there's not a good correlation. For example, here, low tidal height, low performance, high tidal height, high performance. But here, high tidal height, low performance, low tidal height, high performance. So it doesn't seem to be so directly correlated. We then start looking at what's the impulse response look like. So here I have plotted delay on the vertical axis. And so the bright areas are where the arrivals are. So you can see the direct and surface reflected arrivals here. And then here are more multipath that you get in. Now, what becomes apparent is that these direct and surface reflected arrivals, sometimes I see them separate, but sometimes they tend to merge depending on what the tide might be doing. So if I mark these areas where they are separated or they merge, you can see that, so these are separated. So I just mark this and I mark all of these areas. You'll see that every time they are separated, I have low performance. Whereas every time they are merged, I have high performance. So at least I understand where this is coming from. And where this is coming from is when they are separated out, which is shown by the dotted line. The signal to noise ratio is much worse than when they merge together and they coherently add up. So that's basically where the performance difference is coming from. But the question still remains, why do they get separated and merge? Is this because of the geometry of the channel as the tidal height changes? If that's the case, then the same tidal height should give me the same geometry. So if I look back at this plot and I say, okay, this tidal height, I got bad performance. This tidal height, I got good performance. Or yes, the bad performance here, I got a good performance. So that doesn't seem to be the case. So the geometry doesn't seem to explain what's happening. Why do the same tidal heights give me here separation and here not separation? So there were other hypotheses. Maybe it's the geometry because of the buoy motion, but the buoy doesn't move very much, so that doesn't explain it. Maybe it is sound speed changes because of which the distance change makes a larger difference in time. But the temperature in Singapore water does not vary that much, so it explains too little. In fact, if you plot the temperature, you can see that here's a high temperature, which is in a good region, but here's a low temperature, which is in a good region. So the temperature is not the case either. So what else can change the sound speed? The answer to this is bubbles. If you have a very small void fraction, 10 to the minus 5, it's sufficient to induce a 10% change in sound speed. And that's actually enough to explain what we are seeing. Why would we have bubbles? We don't actually have a lot of breaking waves or white capping in Singapore waters, but we do have a lot of ships. And ship wakes have a lot of bubbles in there. One might expect that as ships pass by, a wake comes in and you get lots of bubbles, but a lot of these bubbles either disappear because of buoyancy, they rise up to the surface, or they dissolve away within a few minutes. That's the traditional understanding of it. What I will show you in the next few slides is that's not a good understanding of what happens in busy waters. In busy waters, what happens is that when you have a lot of ships passing by, every time a ship passes by, it injects bubbles. It saturates the water, and these bubbles don't dissolve very quickly. So you get bubble replenishment pretty quickly, and so you get a persistent layer of bubbles. And that's what can lead to a significant impact on communication systems. So once you understand this, you can actually see what happens here. So let's take an example, let's say here, okay? So this is maybe early part of the day when there are not many bubbles in the water because there is not many ships at night. So I have fairly good performance. Then as the tide comes in, there is water from where the shipping channel is that gets brought into the communication channel. And so you get poorer performance here. So let's say here's when there's less bubbles. As the tide comes in, it brings bubbles into the communication channel. And this is, let's say, in the afternoon. So when there's lots of ships, so you get lots of bubbles coming in. At night, as it flushes the bubbles out, you get good performance again. In the morning, as the tide comes in, you get some of these bubbles coming back, but now less because at night there was less shipping traffic. And so you can see this alternate large areas of poor performance and alternate small areas of poor performance. So that bubbles completely explain what's happening here in long term. To understand this better, we actually did some experiments, and this was work that we did with a Grant Dean at the Scripps Institute of Oceanography and one of my students, Gabriel Chua, who worked on looking at the effect of bubbles in communication systems. So we had a wind wave channel where we introduced bubbles artificially and looked at what happens. So the way to read this plot is, here's an area where we didn't have very many bubbles. On the vertical axis is bubble radius. So these are small bubbles, these are large bubbles. And the brighter it is, there are more bubbles in the water. And on the horizontal axis is time. So initially we didn't have very much bubbles. Then we introduced a large amount of bubbles by having breaking waves. And then we stopped creating the breaking waves by controlling the wind. And we let the bubbles decay and observe what happens. So you get this region here where the large bubbles disappear quickly by rising from buoyancy. And then you get a region here where the small bubbles slowly disappear because of dissolution. So there are two different phases through which the bubbles disappear. And what the claim is that these bubbles take a long time. They take many tens of minutes to disappear, by which time ships can inject even more bubbles. And so you can see that these bubbles can persist over many tens of minutes and they can form a persistent layer. So in the interest of time, I won't go through all the details, but another thing I want to point out is if you look at what happens in terms of attenuation, you can see that initially when there are not many bubbles, you have certain signal strength. When you inject bubbles, the signal strength disappears because of lots of attenuation because of those. As the big bubbles go away, the signal strength reappears, and then it slowly goes on increasing as the small bubbles disappear. So the signal strength here and here is not very different. So the bubbles, while they are in the water, they're not causing a lot of attenuation. But you can see that the spread here is much larger than the spread here. So they cause a lot of time variability in the channel, and that affects communication systems adversely. So here's an example where you can look at a constellation when you have very few bubbles, and you can look at a constellation when you have a lot of bubbles in there. So you can see the spread in terms of the phase because of the bubbles. And so having bubbles, while you might not reduce the signal strength, you might increase the phase jitter, and so it has a problem for coherent communication. How long do these bubbles last? It turns out that these bubbles, by a lot of models, you would think that they might last a few tens of minutes. So this is what you would expect. And we did some measurements in a controlled environment where we injected bubbles in salt water and looked at how they compare with models. And you get a pretty good comparison with models. You get few tens of minutes that these bubbles can last for. However, when we put seawater from Singapore Straits in this tank, and we did the same experiment, we found that bubbles last much longer than they last in just pure salt water. And it turns out that this might be because of surfactants that might be present as due to pollutants in the waters. With a lot of shipping, you might have hydrocarbons and oils and things that are polluting the water. And when they coat the surface of bubbles, they inhibit some of the gas exchanges. And this might be making the dissolution time even longer. So some of these bubbles can last hours and therefore cause a significant impact on communication systems. We were able to verify this by actually going out and making measurements next to a shipping channel. So we had a shipping channel here. We put a bubble spectrometer and actually measured it. And you can see that as ships pass by at particular times, a little bit later, we can see big bubble plumes passing through the communication systems as the ship wake, the bubbles created by the ship wake are transported by the currents through the communication channel we have. So the conclusion here is that microscopic bubbles can play a very important role in producing noise, attenuating the signals, but also altering the sound speed and causing phase fluctuations. So there are many different ways in which bubbles affect communication. When you have a large amount of bubbles, noise and attenuation are big problems. These are very well understood problems. But when you have a small amount of bubbles, persistent layer where you don't have a large amount of bubbles, you have small amount of small bubbles, they do have an effect on sound speed, and they can cause phase fluctuations, which also affect communication systems very much. These bubbles can persist for hours, and they can be advected by currents. So you can get the effect of these bubbles at significant ranges, even kilometers away from where the bubbles are produced. So you might be a kilometer away from a ship, and you might still see the effect of that ship on your communication system. So are these unusual suspects just limited to Singapore waters? Well, it turns out not. You can find snapping shrimp in many different parts. Anywhere where you have shallow, warm waters, you are likely to find snapping shrimp. So you might get impulsive noise because of those. But even in places like the Arctic, which are very far away from being warm, you don't get snapping shrimp, but you do get impulsive noise because of bubbles bursting out from melting ice, as well as ice cracking noise. So some of the things that we are learning about communicating through bubbly waters or communicating through impulsive noise may also be applicable in very remote areas, such as communicating in the Arctic areas. So with this, I thank you, and I reach the end of the presentation. Happy to take questions.
Thank you so much for your presentation. Yes, I do see some questions. So the first one, yes, from Professor Akhildis, is about how much the shrimps, I mean, how much the signal to noise ratio is affected by shrimps, and how these compare with other kind of noise, like those generated by ships or by other phenomena. This is the first question.
Sure, thank you. So the answer hopefully might have been evident in the later part of my presentation, but the short answer to it is the snapping shrimp noise in terms of power spectral density. It is loud, but the effect you see on signal to noise ratio is not the only way it affects communication systems. So in terms of signal to noise ratio, there is an effect, but it's a relatively modest effect. If you just consider that, you might think that your system should work quite well. It's the Gaussian noise assumption that fails, which has the larger impact. So if you take that into account, then you can get pretty good communication performance. But if you don't take that into account, you have a significant loss of performance that you get. The second part of the question, which was, does a match filter work well? The answer is, without modification, it doesn't work particularly well, but you need very small modifications, like just putting a nonlinearity such as a sine function, or a nonlinearity such as a clipper, and you can get significantly better performance for very little cost.
Okay, great, thank you. Then another question from Igor Gilin. Could you please elaborate what are the reasons that the shrimp noise has no phase shift symmetry or constellation rotation symmetry?
Okay, so the reason for this depends very much on how the passband to baseband conversion is done. So if you do the passband to baseband conversion using certain methods, so for example, if you did not have the sampling rate is 4 times the carrier frequency, or if it was not an integer multiple of the carrier frequency, what you would get is a constellation that looks rotationally symmetric. Okay? Basically because the direction in which you might get a large deviation can be any direction. However, when you have these particular special conditions, like you have the sampling rate being 4 times the carrier frequency, when you have a large deviation on a particular sample, it either goes in the direction of the real axis or the imaginary axis, because every sample is rotated from the previous sample by 90 degrees. And so that's basically what breaks that symmetry, and you get these 4-tailed distributions. If instead of that you had, let's say, 8 times the carrier frequency was the sampling rate, you would actually get an 8-tailed distribution. You'll get every 45 degrees, you will get these particular ones. So it depends very much on the exact way that you do passband to baseband conversion. So I had taken one example where we were looking at 4 times the carrier frequency being the sampling rate, and that's what led to the 4-tailed distribution that you saw.
Okay, great. Thank you so much. Then there are two more questions about bubbles. One is from Osama Bushnak. Is there a way to deal with the bubbles to mitigate their effects?
Okay, so this one is a trickier question. It's something that we are still working on, so I don't have a very good answer to this, but there are at least a few things that we can do. One of the things that we can do with bubbles is bubbles are, or the dissolution rate of bubbles is very dependent on the size of the bubble. So if a bubble is very small, it tends to dissolve very quickly because of Laplace pressure. If the bubble size is very large, it doesn't dissolve quickly, but it has a lot of buoyancy. So you lose those bubbles because of buoyancy. So the bubbles that stay in the water are of particular size. And once you know that, you can control your frequency band so that you are not at least in the resonant region of that bubbles. And that reduces the impact, at least in terms of attenuation, quite a lot. So what we have found is the typical frequencies which are affected most by bubbles are somewhere in the 25 to 40 kilohertz range, where we see a lot of bubbles in Singapore waters. If you go significantly lower or higher than that, then the impact is a little bit less. So that's one of the things that you can do. The other thing that you can do is to understand when you have bubbles coming in and change modulation scheme or change frequency. So when you have very small bubbles, you may not even have very small number of bubbles out of the resonant frequency. You might not even have a significant attenuation effect, but you might have a phase fluctuation because of that. So in those kinds of cases, you might need to deal with the phase fluctuation by either using a non-coherent scheme, which can allow you to get around it, although we haven't yet developed a good technique to be able to correct for that phase fluctuation.
Okay, thank you so much. Another question from Karsten Wolf. Did you observe more microbubble effects during a specific time, like during the day or at higher temperature?
So for Singapore waters, we don't have a lot of change in temperature, so I don't have a comment on how the microbubbles would be affected as a function of temperature. But we did find time of day to be important, mainly because of time of day affected shipping traffic. So in the afternoons, we had a lot of shipping traffic. So the bubbles were formed in the shipping channel during the day. At night, what we found is that these bubbles were advected around by the currents. And so we had a large effect in the late afternoon towards night. We had a significant effect from the bubbles. Then in the mornings, the bubble population was much lower because a lot of these bubbles were dissolved away. And as the currents took the bubbles away from the channel, we get improvement. But even later on in the morning, if the bubbles are brought back into the communication channels, their effect was much lesser because we didn't have a lot of shipping traffic at night. So there was a diurnal cycle based on how much shipping was around, and also based on what the direction of currents were and how strong the currents were, whether the bubbles were advected into the communication channel or whether they were removed from the communication channel.
Great. So thank you so much. Also from Professor Akildis, thank you so much. And I see definitely that there are many topics in common, so I hope that we can meet soon and maybe start some new collaborations.
Sure. Most happy to explore collaborations, and thank you for organizing.